Everybody hear me okay? So, okay. So as Scott said, I've been a faculty member here for 27 years now, and my research in general focuses on this general idea of surfaces and interfaces. So I'm a chemist by training, spent 5 years at IBM in the physics group. So I'm sort of somewhere between a physicist and a chemist and a material scientist, but essentially the problems that I like to look at are related to surfaces and interfaces, and especially processes that involve charge transfer at interfaces. So think electrochemistry, photoelectrochemistry, energy storage, things like that are generally the sort of the general topics that I'm interested in. So what I'm going to talk about today is some of the work we've been doing in the area of lithium-ion batteries. And so I thought, just to begin with, make sure that everybody understands kind of what a lithium-ion battery is and how it operates. So this is sometimes called a rocking chair battery, because essentially what we do is we kind of tilt the electrochemical potentials in order to favor lithium ions rolling from a cathode over to an anode. And the cathode is typically made out of a metal oxide. So in your cell phone and laptop, it's made out of lithium cobalt oxide. And so this basically has a metal in a high oxidation state, so cobalt 3+ when the lithium is inside. And when you charge your battery, you're essentially applying an external voltage source up at the top. And what you're doing is pushing the lithium ions out of the cathode and over into the anode. So the lithium ions that like to go over into the anode, which is typically graphite. Graphite is a sheet-like compound, so the lithium ions like to insert themselves into the sheets, and they more or less form a stoichiometric compound, LiC6. And as this cobalt pushes the lithium out, the cobalt is oxidized from cobalt 3 up to cobalt 4. And then when you use the battery, everything kind of reverses. The electrons get pushed out through your laptop or cell phone, the lithium ions move back, and you basically go back to where you were before. Okay. Let's see. Now, what I've been interested in for the last few years has been understanding what are the things that limit the performance of lithium-ion batteries. And the thing that we focused on mostly is the idea of lithium-ion battery safety. So I think you all know you cannot take charged lithium-ion batteries into your checked baggage on an airplane. You are probably aware of the Dreamliner fires. So this is the battery pack from the Boeing Dreamliners, and that when these caught on fire, the entire Dreamliner fleet was grounded for about 6 months, I think was the total time before they kind of solved the battery problem. There have been other pretty severe battery fires on airplanes that you probably have never heard of. They've usually been cargo planes, but this is a cargo plane where it was later traced to that cargo plane had a set of lithium-ion batteries on the inside, and those caught on fire during flight, and basically that's the result. Some people think actually the Malaysian Air fire, the Malaysian Air plane that disappeared, that was carrying a load of lithium-ion batteries, and there are theories, I don't know whether they're well-founded or not, that part of what might have happened there might have been battery fire that released noxious fumes that might have knocked the pilot and co-pilot unconscious, and thereby rendered that plane in not such great shape. So, okay, so if we look at the lithium-ion battery a little bit more closely, I also do a lot of work in the nanotechnology area. So Scott mentored, I run something called the Center for Sustainable Nanotechnology here on campus, and I'm not really going to talk about that very much, but that's a large grant. It involves 12 different institutions. It's $4 million a year. It involves about 70 people at these 12 institutions trying to understand nanomaterials related to energy storage. And so again, some of the things that are happening in the battery field is everybody would like to have a battery that can be charged or discharged more quickly. And so if the lithium ions have to go a shorter distance, that means you can charge the battery more quickly and you can discharge it faster. And so that's driving a tendency to go toward various kinds of nanoscale materials like silicon. So silicon can be grown in the form of very small nanowires that are only about 100 nanometers in diameter. And if that lithium then only has to go a very short distance, you get, in principle, very high rate. And then it turns out that the amount of lithium that can be stored in silicon is about 10 times that of graphite per unit weight. And so that's driving a change there. And then over on this side, I mentioned that lithium cobalt oxide is the material in your cell phone, your laptop, especially as we go toward large-scale energy storage, so meaning primarily in the form of electric vehicles, for example. That becomes very cost sensitive. So if you're going to spend $1,000 for an Apple iPhone, you probably don't mind paying 10 bucks more for a battery, right? But if you're buying an electric vehicle, the amount of battery that you need becomes a pretty significant cost, or a fraction of the cost of the vehicle. And so that's driving a tendency toward lower cost materials and also more sustainable materials. There are concerns about the worldwide supply of cobalt as well as lithium, and whether one can meet that. But the bottom line is that's driving a tendency to look at other kinds of materials that replace cobalt with nickel and manganese. So this leads to a class of materials called NMCs, nickel, manganese, cobalt. So the recent issue Nissan Leafs and a lot of the other electric vehicles now are moving away from other metals and going toward these nickel, manganese, cobalt. And if you're lucky enough to have a Tesla, that is a nickel, cobalt, aluminum alloy that's used in the cathodes there. Okay, so there's a lot of activity in the energy storage area in terms of new materials. A ton of that effort is focused on new cathode materials, some on new anode materials. But if you look at the amount of energy storage per unit weight, the energy storage capability of the cathode is primarily the limiting factor. And so that's driving more and more activity here with different materials, nanostructuring in order to get high rate. My focus actually has been somewhat on the anode and cathode, but also on the lithium conducting electrolyte. So again, if you think about how does a lithium ion get from the anode to the cathode and back, there's an organic fluid in here called an electrolyte. So an electrolyte is a combination of a solvent and a salt. So the salt is a lithium compound that basically dissolves in the solvent and provides a way of shuttling lithium ions back and forth. And so this lithium ion conducting area turns out to be important. And the limitation here comes from the fact that while I sort of drew an idealized battery, in practice there's lots of bad things that happen. So I mentioned already that graphite has relatively low capacity and relatively poor stability. One of the challenges on the anode side in particular is that when we think about how does lithium move back and forth, the lithium in these organic compounds is solvated, meaning that the lithium is surrounded by molecules of the solvent. And in a typical lithium-ion battery, like in your cell phone and laptop, the primary solvent component is this molecule right here, dimethyl carbonate. This molecule is very oxygen-rich. The richness of the electron density around the oxygens provides a way to bind to the lithium, and they basically allows the lithium to move back and forth. But there's a problem that when you charge the battery, when you charge the battery and the lithium tries to go in between the sheets of graphite, it basically strips off some of the solvent, and that solvent reacts on the surface of the electrolyte and forms something called an SEI layer, solid electrolyte interface. Okay? So in fact, if you go back to the invention of the lithium-ion battery in 1961, the key development in the lithium-ion battery that finally made it possible to have rechargeable batteries was, in fact, a chemical way of stabilizing the formation of this SEI layer in such a way that it could conduct lithium ions back and forth, but would not allow solvent molecules to go through. If these solvent molecules get between the sheets of graphite, they push the layers of graphite apart. It's called exfoliation. The little layers begin to come apart, and the electrode basically crumbles, right? It just falls apart mechanically because of the mechanical stresses. So in fact, the reason when you get a lithium-ion battery or whatever it is, your recent device, and they tell you always charge it up the first time before you use it, right? The reason that you are doing that is you are making sure before you use the battery that you have formed a good SEI layer. So the manufacturer does this for you already, but just to be sure that it's really good, you charge it up all the way the first time. And by the way, the reason that you should never discharge a lithium-ion battery all the way to zero is that this layer begins to degrade when you completely discharge the battery, and it won't reform properly, right? So that really is the key to the stability of the battery. On the cathode side, we have some chemical instability. In particular, lithium cobalt oxide has a fundamental instability that if you try to remove more than half of the lithium, you get this compound here. And this compound actually wants to fall apart to a different compound and produce oxygen. Okay, so now you've got a problem that this compound also is an insulator. And so if you overcharge the battery in particular, meaning that you remove more than half of the lithium, you change the composition, you turn it into an insulator, then the next time you try to charge the battery, it's highly resistive, you build up a lot of heat, and you have oxygen plus heat plus flammable electrolyte. This thing is highly flammable. It has a flash point below room temperature, meaning that if that electrolyte sees a flame or any significant high temperature, it will catch on fire. Okay, so the combination of fire and oxygen is not really, so you can see why you shouldn't take this on an airplane, right? Kind of makes sense, okay? So the other challenge is that when the electrolyte interacts with the cathode, there can be a chemical reaction here. And in particular, these molecules, you can see, are mostly carbon and oxygen. And so when these decompose, they produce primarily CO2. It's this wonderful term called gassing. But if you ever take your laptop to the Apple store, which used to be at a Westtown Mall and I guess is now in the Hilldale Mall, one of the first things they'll do is they'll look at the bottom of the laptop. They'll look at the bottom of the laptop and look and see if it's bowed out, okay? Because as the battery degrades, or if this electrolyte begins to degrade, it produces CO2. The battery packs are basically like aluminized baggies is the best way of describing it. You have an anode and a cathode with the electrolyte in between, and it's sandwiched together into an aluminized, flexible plastic bag that then begins to bow out if you degrade the electrolyte and start producing CO2. Now, you might think that would be good, making the CO2 as being like a fire extinguisher, right? But it turns out that that is bad because now your battery actually has pressure buildup on the inside, and that pressure buildup can create lots of problems downstream that are not particularly good. Okay, so a lot of my work has been focusing on the idea of trying to replace these electrolytes, like this compound, DMC or dimethyl carbonate, with a new class of compounds that are based on molecules that look more like this. These are generically what I'll call organosilicons. And so these compounds always contain one or more silicon atoms. And then they contain some other kind of group over here that is always electron rich. So instead of these kinds of electron rich groups, we use something that's more like an oxygen, carbon, carbon, oxygen, carbon, carbon, oxygen. These little molecules can kind of wrap themselves around the lithium. They can chelate to it, complex with it. So this part of the molecule interacts with the lithium and solvates it, basically hugs it so it can carry it through the electrolyte. This end of the molecule does some really interesting things. The silicon atom increases the dielectric constant. So it turns out the solubility of lithium in an electrolyte increases as the dielectric constant goes up. So one of the roles of the silicon atom is to increase the solubility of lithium. This also has some other properties that we don't completely understand that have to do with radical reactions. So most of you are not chemists, but basically radical reactions happen when you have a terminal group that has an odd number of electrons. In general, radicals are highly reactive. And so if you replace that silicon with a carbon, you make something which is much more reactive than having the silicon atom on there. Okay, so it's kind of a generic design scheme where we think about having a dielectric that is an insulating lithium complexing group. We've got maybe some spacer groups, and then this end over here, which is the silicon containing end. Okay, so the electrolyte is really the biggest problem overall in terms of both performance and safety. So I mentioned that people are trying to go toward new kinds of cathode materials based on things like nickel and manganese instead of cobalt. Turns out that as you go away from cobalt and go toward nickel, you also make that cathode more reactive. And so stabilizing the reactivity of the electrolyte at both the cathode and the anode surface is really the thing that limits the performance of lithium-ion batteries. So as much attention is being placed on the cathodes, the electrolyte is really the fundamental limitation. Okay, so again, the idea that we have been working on is trying to replace these conventional electrolytes like dimethyl carbonate with this other class of compounds like this one, where we rely on these oxygens to wrap themselves around the lithium and complex with it. The silicon has kind of multiple functions, high dielectric constant, it lowers the vapor pressure, it makes it less flammable, and has some other properties as well. Okay, so I started in this area in 2006, right? And what happened in 2006 is a colleague of mine, Bob West, who at that time was, I think, 80, approached me walking down the hallway, all right? And he basically said, Bob, we're both Bob, it's confusing, do you know anybody who does electrochemistry? And I responded, well, yeah, we do electrochemistry all the time. And he came back and said, well, he's got these organosilicon compounds that he thinks are interesting for lithium-ion batteries. And at that time, Bob had been working a little bit with Argonne National Laboratories and a small company called Qualion to develop a whole series of molecules that sort of have the same general bonding motif, sort of a silicon atom with some stuff decorating it. Some of these, what are called ethylene glycol groups or polyethylene glycol groups, and you can have the silicon in the middle, or you can have it on both ends. You can basically arrange this, and you can have these chains of different length, but fundamentally they were based on that motif. Up until that time, I had actually never worked on lithium-ion batteries, but I'm a materials guy, and so I had been working for a number of years in various kinds of nanomaterials, and one of the things I had been working with are these carbon, this nanoscale form of carbon called vertically aligned carbon nanofibers. And these are little carbon fibers, or the open sheets, the place where the lithium ions can intercalate in, are along the edges of these little rods. And I thought, well, if you wanted to make a battery that could be really charged and discharged quickly, this is almost ideal. You've got this long rod, but the lithium only has to go a little ways. And so these would maybe be ideal anodes for lithium-ion batteries. And so we decided to, think about partnering. So he was interested in starting a company. That was his idea. And I decided, sure, why not join it? Okay. So since then, we've been working together for the last, 11 years now. And Bob is basically the organosilicon synthetic chemist, and I provide most of the expertise on the materials science and the electrochemistry side. And so we actually have very complementary interests. And so the rest has been working together. So back in 2006, we decided to form this company, which was originally called Polyron, right? And so I don't know how many of you know how you get small companies started, but a common way is to go to an agency like the National Science Foundation. Every federal agency is required by law to reserve some of their federal allocation to be used to support small business. And so usually this is done through what are called SBIR, Small Business Innovative Research, or sometimes STTR, technology transfer. Okay? Both of them are ways of providing small amounts of money, so $100,000 really doesn't go very far, to start the company. So we started by founding this company back in 2006. We originally called it Polyron. There were some complications that I won't go into. I came up with the name Silotronics for silicon, silanes, or silicon-containing compounds, and electronics, so silanes for electronic applications. And so in these SBIR grants, most of the money goes to the company, but some of it can come back to the university. So as a faculty member, you're allowed to wear two hats. You can, to some extent, be involved in a small company and retain your full-time position as a faculty member within reasonable limits, and provide you follow all these federal guidelines and university guidelines. So that's essentially what we do. We founded the company, we subcontract some of the work back here to UW-Madison, set up intellectual property agreements, and the role of a phase one grant is really to identify whether the idea that you have is a technical possibility, and whether you can come up with some kind of a business plan that, if you're successful on the technical side, is there a hope that there might actually be a business case for what you're doing? Okay? And these are typically, they used to be 6 months long, now they're a whopping 9 months long. Still not very much time and not a lot of money, but often enough to get over this kind of initial proof of concept as to whether things will work. So back in 2006, we set up our first very sad little laboratory. We got everything off of eBay we could. So we got a fume hood, batteries are very, very sensitive to water, all right? Not so much to oxygen, but water is a real killer. You'll see why in a little while. But so that means everything has to be done in a dry box. We got this sorry little glove box from eBay. We still have it, actually. We still use it, but not for that. A little oven to be able to control the temperature. And then the best thing we did was we got this guy, Mike Polina. We did not get him off of eBay, right? We got everything else off of eBay. But Mike actually got a master's degree in renewable energy from, I think, Michigan State University. And he was an absolute jack of all trades. I don't know if you remember many MacGyver. Any of you ever seen MacGyver? Right, an old movie, like guy who could turn a piece of shoestring into a nuclear bomb. Mike could basically turn a hunk of junk. He could turn a jumpy $5 junk oven into a highly precise temperature-controlled battery tester. The guy's just amazing. He was with us for about 8 years, and then his wife got his degree in veterinary medicine, and they moved away. So here's our laboratory today. So we've grown up a lot since then. We still have a pretty big laboratory. This is now across from, if you ever out at the Midby Theater out at MATC near the airport, we're located right across from that. A large chunk of this building is Virent, which many of you have heard of. We are the rest of the building is Virent. So we're a laboratory that holds, right now we have about between 15 and 18 people, depending on how you count them. Here in Madison, and then we opened up a branch office in Tokyo, Japan, about a year ago. So if you want to be in the energy area, there is no significant battery manufacturing in the United States. It is essentially all done in Korea, Japan, and China. And so if you want to do something in the space, you've got to have boots on the ground in Asia. And so a while ago, we opened up a branch office in Tokyo. So here's most of the people who are involved. This is a few years old, but so Deb Gilbert came. She used to work at Rayovac, which is out on the west side. Bob West, my co-founder. Monica here was the first company employee. She started as a postdoc with me and then transitioned over to the company. Mike Polina, our first non-PhD employee, and then some PhD students and other people involved. Our CEO, Mark Zager, who's been with us since 2007. Just if you've ever seen a little SBR or what a startup company looks like, again, everything has to be done in these glove boxes. We have these banks of glove boxes with gloves sticking out, and people have to work inside of those. People aren't inside. They stick their hands inside. And then a lot of it is temperature-controlled ovens so that we can do electrical testing. Most of the work we do is done in coin cells, so like a watch-sized battery, right? And it turns out that's not particularly great for testing long-term stability, but a lot of what we need to do is understand the fundamental electrochemical performance of these electrolytes and how they compare with typical materials, and especially given the fact that synthesizing and purifying these materials in small quantities is very expensive and very time-consuming. So the idea that you can do it with a very small amount of material turns out to really help you get over the hump in terms of evaluating things, and allows us to test a lot of materials relatively quickly. Recently, we've graduated up to being able to test in what are called pouch cells. So these are cells that are maybe 2 inches by 3 inches and are essentially what you'd have inside your cell phone. Okay? So that's about the size that we typically test on. Electrolytes done in sort of 10 to 20 liter quantities. We've recently scaled up now, so we're working in pretty much large quantities. So I'm just going to summarize 10 years of work in one slide, all right? And then I'll kind of come back and tell you what happened along the way. So when we started off, I told you we started with compounds that looked like this. It had a silicon atom, had this ethylene glycol chain, and had some decorations maybe on the silicon in terms of various kinds of chemical functional groups that alter the performance. This set of compounds really didn't work very well, and I'll tell you why. But it led us to doing a generation 2 compound. Now, actually, the transition from generation 1 to generation 2 was largely based on computational work that I did. So within the computer, you can pretty easily calculate, if you have a molecule, where should its highest occupied molecular orbital and its lowest unoccupied molecular orbitals be in energy. And what that allows you to do is to assess the electrochemical stability toward oxidation and reduction of the molecule. And so what I did was I played around with changing the structure of this and asked pretty much, could I design a molecule that had a wider range of electrochemical stability? And that in part led to this molecule. Okay? so-called generation 2 compounds. And generation 2, I'll show you, actually works pretty well, but we had a completely unanticipated discovery with generation 3, which are molecules that basically look like this. Again, silicon atom, maybe a fluorine on here, and instead of having this ethylene glycol group, have what's called a nitrile or a cyanyl group on there. Okay, so we've changed the nature of that lithium complexing group. So this set of compounds had a completely unanticipated benefit, and the result of that is we've scaled up, and over the last few years, we've had about $10 million in investment in the company from Hitachi Chemical, Inabata company in Japan, and basically looks like we are completely scaling up and very likely that we'll be incorporated into consumer products within the next year. So if we go back and say, well, how do we characterize the performance of a battery? There's lots of ways of doing that. The main way of doing it is simply to charge the battery and discharge the battery. Again, the first couple times you charge the battery, you use slightly different parameters, and that again is to make sure that this SEI layer forms very well and forms completely. So you don't have to really worry about that. But then effectively what we do is we look at how much energy can we store. So milliampere hours is charge. It's current times a time, so that's a charge. And we normalize it by the weight of the cathode so that we basically account for variability in the cathode mass between different samples. And what we essentially do then is characterize how does this vary as a function of the number of charges, and we can do it at different rates. And again, I won't go into here. Sometimes we swap out the electrolyte if we want to understand if the electrolyte itself is degrading versus the cathode is degrading. One thing we can do is charge the battery for some number of times, tear it apart, put a new electrode, and restart the system. Okay, that turns out to be pretty useful. So ideally what you want is you want the discharge capacity and the charge capacity to be essentially identical. Any difference between the blue and the red means you're putting energy into the system that you're not getting back. Where does that energy go? The only place where energy can go is into unwanted chemical reactions, right? So anything that is less than 100% efficiency in a battery means that you're inducing chemical degradation that you have no way of recovering from. Now, a typical consumer battery is typically designed to be charged about 300 times, right? So basically, your iPhone, if you charge it every day, it will last about 1 year before the battery fails, okay? And that is really just a result of the fact that you always have some of these uncontrolled reactions that are taking place on the anode and the cathode. So the goal then is to make this as perfect as possible, okay? Now the problem, I mentioned that this generation 1 set of compounds, here again is a little list of these, turns out not to work very well. And the challenge with the lithium-ion battery stability, as much as it's due to the electrolyte, so this is the solvent. Remember I said that an electrolyte consists of 2 parts, a solvent, which are these molecules, that's the liquid part, and then a salt. So we have a salt of lithium, so it's got a lithium cation, and then some kind of an anion, PF6, Libog, bisoxoborate, it's not named after me, and TIFC trifluorosulfonamide, which is this compound here. So it turns out for various reasons, lithium PF6 is the only economically feasible salt to use. These two exist, but they're very difficult to purify, and the cost of that salt becomes pretty significant. And so lithium PF6 is always the salt that is used in all commercial lithium-ion batteries. So PF6 has a problem, which is that it can decompose into basically is in equilibrium with PF5 and the fluoride ion, okay? And the problem with PF5 is that it can react with trace amounts of water to produce a range of different phosphorus oxygen compounds, but the main problem is it produces hydrofluoric acid. So POF3 is pretty nasty all by itself, but HF is even nastier, okay? And you can see what's happening. So one of the ways that we characterize what happens to the electrolytes is we do a huge range of analytical measurements, but one of the things we do is characterize what happens to the electrolyte as we begin to heat it up. And so the way we do this is we have a little mass spectrometer that has kind of like a hollow core optical fiber connected to it. So it can basically sample directly from atmosphere, right? Directly from atmosphere into this mass spectrometer. And then we make something that's like a little battery. And essentially what we do is we either drive the sample electrochemically and look what gases are involved, or we simply heat it up and look for evidence of thermal reactions. So at some point, this lithium PF6 will begin to react with the electrolyte, and when that happens, it begins to evolve various degradation compounds. And what you can see is if we start with this compound, for example, this got a fluorine here, that we begin to see products that indicate the molecule is somehow cleaving, like right here. And we see that because we see products like we have an F-methyl silicon, and we see an FF methyl silicon. Well, where did the extra fluorine come from? It came from the HF. And then this compound can undergo a number of different kinds of degradation pathways, but it results in things like dioxane and other compounds. And so one of the things we do to characterize the overall stability of these compounds is to look at these thermal degradation as sort of like an accelerated aging and say, well, how does this degradation vary as we change the structure? So this OS3 is that third set of compounds where we replace the ethylene glycol with a nitrile group. And if we do that, you now see that there's much less evidence of degradation even at 175 degrees centigrade. Okay? So we can basically use ideas like this to characterize the degradation and ideally optimize the electrolyte separately from the battery. We have these little codes we use to designate sort of what the structure is, but that's not super important. Okay, so the challenge here then is that this sort of Gen 1 set of compounds didn't work well, not because it was intrinsically bad, but because you always have a little bit of HF present. And the challenge here is that you can make an electrolyte really, really dry. So a typical battery-grade electrolyte has about 30 parts per million of water in it, which isn't very much. But as I'll show you later, this is what's called an autocatalytic reaction, meaning that the HF produced by the reaction with water, so we have this PF6, it produces PF5, PF5 reacts with water, that produces HF. HF degrades the compound. The products of this are themselves electrochemically active and unstable. So you get this kind of snowball effect that once you begin to degrade a little bit, the whole thing just rapidly begins to totally tank. Okay? And so this is a problem. So one way of fixing that, well, here's an example of some of the other things we do. We do mass spectrometry. Here's an example of what that looks like. It's kind of like a home-built little coin cell. We measure the mass spectrometer. We use traditional electrochemistry to look for the onset of degradation. We also do a lot of work characterizing what happens to the surfaces. So if there are degradation products, some of those obviously form and go into the gas phase or into the electrolyte, but we also learn a lot by analyzing what happens to the electrodes. So the main tool for characterizing that is a technique known as X-ray photoelectron spectroscopy, where we look at what happens to the core levels. So this, for example, is a carbon 1s level, so we can clearly see evidence for carbon in different chemical forms. And we also use techniques like Raman that are available to us as well to characterize what's going on. So it's really piecing together a lot of different things. So, okay, so if this compound has a problem, what we decided to do was introduce a second generation by saying, well, instead of having the silicon oxygen, so we have the fluorine like to attack here, the hydrogen like to attack there. If we put in some spacers in between, maybe we can stabilize the structure against degradation. And that actually turned out to work. Okay, that actually helped a lot in terms of stabilizing it. Most of our recent activity has been with a slightly different version that we simply call our Gen 3 compounds, where we both introduce the spacer, which stabilizes this part of the molecule, and then introduces this nitrile group in order to complex to the lithium. So now in this case, we begin to get really good performance. So here, for example, is a carbonate control. Again, looking at these charge and discharge, you can see they're exactly overlapped for carbonate. Carbonate actually works pretty well. It's been optimized over the last, 40 years, since 1991. If instead we use one of these, so this is the Gen 2 compound, and this is the Gen 3 compound, you can see that we can get performance that is at least as good as one can get with a traditional carbon electrolyte. So we're actually making the battery better, we're making it more stable. The home run that we had was due to a completely unanticipated benefit. That we originally, when we formed the company, we basically went in with the assumption that we were going to replace these carbonate electrolytes with these silicon-based electrolytes. And the problem we faced was that the battery industry is extremely conservative. And so the idea that we would take an electrolyte that had been successfully used since 1991, and that we would replace that with something totally new, right, was more or less a non-starter from the standpoint of commercialization, right? Unless you had like a niche market or you were trying to make very specialized batteries, no large-scale manufacturer was going to put this stuff into a car where the batteries really need to last 10 years, right? 10-year warranty is pretty typical for the battery pack of an electric vehicle. So, but there was an unanticipated benefit, which was that we discovered that if we put only about 5 to 10% of these compounds into a traditional carbonate mix, it completely stopped this gassing problem. That is, this blowing out or release of gas, the decomposition of the carbonate electrolyte, which is really surprising, right? You'd think if the electrolyte is still 95% carbonate and you throw in 5% of this organosilicon compound, you wouldn't really expect that would stop the decomposition of the carbonate electrolyte itself, right? Not unless you got a higher. But this turns out to be the home run. This is why actually we are now commercially successful, is a completely unanticipated benefit. So what does that mean? It means, number one, that you can stabilize and make the battery work not just as good as a carbonate mix, but you can actually make it better because you've stopped those electrochemical reactions that are happening on the electrolyte. Moreover, because you no longer have this problem, you can also operate the battery at a higher temperature. So in fact, a lot of what we do, I showed you earlier the thermal stability, and that if you looked at the mass spectrometer and looked at the evidence for decomposition products, that you could heat this up substantially higher temperatures before you begin to see reaction. In fact, we now take these samples and we put them into NMR tubes, so nuclear magnetic resonance, widely used chemical tool for analyzing what happens. We've had these electrolytes that have been sealed in NMR tubes for more than 2 years and stored at elevated temperatures as high as 100 degrees centigrade. And every few months we go back and check them, and they're like rock solid stable. So it's pretty amazing that the use of these new electrolytes basically completely kills off this gassing problem. Okay? So in fact, we just had a nice little paper published. One of the great things about kind of working between the university and the company is I can play a dual role. So with the company, I sort of work on the technology side. At the university, we do all this fundamental work trying to understand the detailed mechanism. And so this is a nice little paper that was published a couple of months ago outlining why does this work, right? And here again is another example. Here's going up to 5 volts, okay? So going up to higher voltage, higher temperature, and pretty much all of these things work incredibly well. So then the question is, why does it work, right? It's not enough to know just that it works. And again, this is because the battery industry is very conservative. So if you show them you've got some amazing result, that's great. But if they don't understand why it works, you're not going to go anywhere, all right? And so we spend a lot of time trying to understand what's the mechanism of decomposition of these reactions. And so again, this PF6 like to decompose to fluoride ion or LiF, and PF5 reacts with water to produce compounds like this and generates more HF in the process. That HF comes back and reacts with the electrolyte, begins to decompose it. These can also be on to react with more water and produce more and more HF, and this just becomes autocatalytic, and pretty soon the entire thing begins to break away. So what we've been looking at then is how do we understand the decomposition pathways of these various intermediate compounds and try to understand what's happening. But the key is that even though it's the electrolyte that's decomposing, like the carbonate in the carbonate mixtures, these things react with these carbonate electrolytes to produce these various phosphate species, the CO2 that causes the gassing problem, and RF is just the organic part that was over here, whether it's ethyl or methyl or whatever. Okay? Okay, so how do we do this? What we do now is we begin to use NMR. So nuclear magnetic resonance, I think all of you are familiar with at some level. It basically measures the nuclear spin. Most people will use NMR to look either at hydrogen, the proton, or sometimes to use carbon-13, or if you're in the biological field, once in a while you can do nitrogen. We tend to use it to actually look at fluorine. So the isotope of 19 fluoride is abundant enough that we can use it to probe the fluorine in all of these species. And what that allows us to do is to generate a spectrum that allows us to identify what are all of the decomposition products that are formed from these different electrolytes. So here is again a diethyl carbonate, ethylene carbonate mixture, and you can clearly see that you have a lot of these different decomposition products. If you go to this Gen 2 compound where we put in a, well, it's a silicon, and we've replaced the oxygen with this 3-carbon spacer, you have dramatically reduced the number of decomposition products, and you have something which is really clean. And if you replace this group with the nitrile group, now you can see that, in fact, you've really made this thing really incredibly stable. In fact, there's only evidence for one small decomposition products. So and the important thing is that this basically becomes stable. It does not initiate this autocatalytic decomposition process. So you get a little bit of product, but the key is that that's stable. So in these compounds, again, one way that we characterize that is to look at what happens to the PF6 salt. So this is the starting material. And if this is decomposing and being reacted away to form all these other products, we can simply track that by measuring how much of this PF6 is left. And so if we do that, we can take a dimethyl carbonate, diethyl carbonate, ethylene carbonate mixture. Ethylene carbonate is also a very good electrolyte, but it's a solid at room temperature, so it has to be used with either dimethyl carbonate or diethyl carbonate. What we're looking here is how much of the PF6 decomposes as a function of time, either if we don't intentionally add any water, so that would be like a baseline water contamination level of maybe 30 parts per million, something like that. And then just to accelerate that, we often will add a little bit of water so that we know how much water is there, and then we, again, see a very rapid decrease. So again, the key here is that only a few tens of parts per million of water, because this reaction is autocatalytic, can very quickly degrade 30 or 40% of the initial salt that's present, right? So in order to work in that kind of environment, you'd have to really get rid of all the water, or you're always going to have this kind of fading problem. And actually, when we seal these in tubes, in fact, a lot of these samples broke because the CO2 would be released, it would pressurize the internal tube, and they would literally explode on us. Okay? Here's an example using one of these Gen 2 compounds with the ethylene glycol chain. Now you can see that it is much more stable. There's a little bit of initial decomposition, but unlike this case where it continues downward, even if we add 1,000 parts per million of water, we get a little bit of degradation, and then it's basically flat, meaning that whatever is happening in that first section leads to products that are electrochemically and thermally stable. So even if they're there, they don't seem to be doing anything bad. Right? We just ignore this one last point. That turns out to be an errant data point. And then if you look at what happens if you replace this with the nitrile group, now you get something which is just absolutely rock solid stable. Right? So going up to 500 hours, these are held hot. These are at 100 degrees centigrade, all right, well above where you normally want to operate a battery. And in fact, we can see that we can basically shut off all of that decomposition. So this is a big deal, right? Because one of the problems with the lithium-ion batteries is that if they get hot, I don't know if you've ever taken your cell phone and left it sitting in the sun, but if you're in Arizona and you've got a car that's going to be sitting out somewhere in the sunlight, you know, it could very easily get up to 100 degrees centigrade. This compound, I'm sorry, the dimethyl version of that boils below room temperature. I'm sorry, it boils slightly above room temperature. It's flammable even at room temperature. So the idea that you can make these that are now stable up at 100 degrees centigrade really makes all the difference in the world. So we can, now we also look at what happens if we do other kinds of decorations. So I showed you the example with silicon with 1 fluorine. We do a lot of work trying to understand how do things change as we decorate what's on the other side of the fluorine. Does it matter how many fluorines we have, if we have 0 or 1? And there are some differences there. I'm not going to go into what those are. But So again, the key here is that these compounds essentially may form some initial products at the very beginning with water, but these continuing reactions basically get shut off. So instead of having this massive decomposition products, we pretty much just have our parent compound and maybe a little bit of an initial breakdown product, but these are now stable in that, and therefore we basically eliminate all further decomposition. So needless to say, this is a really complicated soup, and so a lot of what we've been doing is trying to work out the entire molecular pathway that is involved in all of these decomposition reactions. So we also look a little bit at, I'm pretty much done here. Also, one of the other things that we can do is look at, I mentioned that this lithium chelating group, either the 3 oxygens or the cyano group, I said that it solvates the lithium, right? And it turns out that solvation is also very important. I mentioned to you that in the case of the carbonate electrolyte, that there's this layer called the solid electrolyte interface layer. And that one role for that layer is to strip away the solvent in such a way that the lithium can go into the graphite without trying to pull solvent molecules with it. If that lithium tries to pull solvent in between the sheets of graphite, the graphite flakes expand and they break, okay? So understanding the thermodynamics of how do these different groups interact with the lithium, you want the interaction to be small enough that they are functionally carrying the lithium between the anode and the cathode, but you'd also like that solvation or that interaction to be weak enough that when the lithium goes toward the SEI layer, it can actually easily remove those solvent molecules to go through the SEI layer and then into the carbon. So we can actually look at that using techniques like infrared spectroscopy. So you can see that this is looking at the carbon-nitrogen stretch of the cyano group. So that is a particular infrared frequency. And if that is in a free solvent, or if it's interacting with the lithium, it shifts the vibrational frequency of that cyano group in a way that we can begin to understand what's happening to the solvation. And that also turns out to be an important result. I showed you that when we looked at the charge-discharge curves back here, we actually had better performance with our compound compared with the carbonate control. Part of the reason for that is that we have less resistance at that electrode interface, and the less resistance is a result of the fact that the lithium chelation with the molecule is a little weaker. And therefore, when the molecule goes to go out of the solution and back into the electrode, it's a little easier. And so that results in less resistive losses at the electrode interface and ultimately makes it more stable. So the bottom line is that we can use this idea to make electrolytes that have comparable or even better rate performance than a traditional electrolyte, get higher thermal stability, we get less gas generation, and all of this ties into higher electrochemical stability so that we actually get performance that exceeds that of an existing lithium-ion battery. It also has wider window of electrochemical stability. So trying to go up to higher voltage, one of the big trends in the industry is to go away from 3.1 volts, which is a typical lithium cobalt oxide, pushing toward 4 volts or 5 volts. The higher voltage you can make the battery work at and have it be stable, the more energy stored per unit weight. And given the fact that there aren't a lot of other schemes to increase capacity, that's when it turns out to be quite important. So I won't go into the rest of this. We also make things that operate at high temperature, kind of specialized things. These are batteries that can operate up at around 150 degrees centigrade. So for the military, there's another kind of chemistry called lithium CFX. So CFX is like Teflon, carbon, fluorine, with acts as some variable composition. It's the battery chemistry with the highest energy storage per unit weight of any known chemistry. And it's quite expensive, but it's used a lot by the military, because if you're going to have a soldier going out in the field, they may not be able to recharge their batteries. They need to be able to hang on to that for a long time. You'd really like to have something that's non-flammable, so if they get hit with a bullet or shrapnel or in a desert in Iraq, that they don't have to worry about their batteries catching on fire. And so we also have been able to show that we've been able to make things that are quite stable. And a result of this is we've got a contract now to put these organosilicon compounds into a helicopter. So we've got a grant from the Navy to put it into a Navy helicopter, hopefully by the end of next year. All right, so anyway, that's it. The student who did most of the work here is Sarah Giel, represented right here. And other people here again is Electronics, a more recent picture with more of the people with fuzzy. So anyway, that's it. I hope that was helpful to you, and I'll be happy to take any questions. Yeah.
So, is anybody, are you aware of any work investigating the problem of solvent degradation from sort of the opposite perspective as far as like altering the spacing of graphene layers or trying to come up with more robust problem pictures?
Yeah, well, it's certainly true, and this is one thing that surprised me is, we say graphite, but graphite A is not the same as graphite B, right? I mean, graphite is dissolved, is made typically from natural products, so a lot of times from coconuts, for example, is a common source of the materials for use for graphite. What ends up happening is the presence of small amounts of different species within the graphite, like oxygen or other things, does change the layer spacing, right? And that has pretty big effects on the performance. That's very black art, I would say. I mean, you can measure an interlayer spacing with like X-ray diffraction, and you can kind of correlate that a little bit with reactivity. But I would say that's pretty poorly understood in general in detail. But I mean, in principle, yes, people do tune the properties of the graphite. And in fact, every manufacturer is graphite. If you go out, I mean, one of the things that, we struggle with as a company is you would think that a lot of these things would be generic, that if you tested it against a lithium cobalt oxide and against a graphite, that those would be the same, whether that was from Hitachi or Sony or Apple, right? But in fact, everybody's chemistry is a little different. Every graphite is a little different. Every lithium cobalt oxide is a little different. Oftentimes there are proprietary surface treatments that are applied to the cathode and anode materials to try to stabilize these. So, it's amazing if you actually look what's inside a functioning battery and the things that are done to make it work. I am amazed that it ever works at all, because there are, a typical electrolyte mixture could easily contain 10 different compounds. It'll contain a little bit of pixie dust to solve this problem, which introduces another problem. So then there's a new kind of pixie dust that gets put in to solve the second problem, right? And it just becomes these really complicated soups. And that's a real challenge, because it means people really lack a fundamental understanding of what's going on inside the cell. And that compounded with the fact that, really what you'd like to be able to do is characterize chemically what's happening right at the electrode surface as it's being charged or discharged, right? So that idea of doing in situ chemical analysis in order to understand what's going on, that's a real challenge in the field. Yeah, hi.
Thanks so much for coming
Yeah,
today.
sure.
So I'm curious how Hitachi is choosing to commercialize your technology. So how are they deciding, going through the testing process, where they're deciding to place it in terms of which batteries and how they're scaling it up?
Yes. One thing I've learned is Japanese companies are like black boxes, okay? They tell you very little, right? What they do is they tell us if they're getting good results, okay? And in this case, what happened was actually we had an agreement with Sony, and we went quite far down the road with Sony to the point of making it into a pilot plant. And then a couple things happened with regards to Sony. The company fell on some hard times, and effectively what they did was they basically changed their management structure, and they suddenly became more conservative in this. Well, they had a battery chemistry that they were trying to commercialize, and it didn't go. They had problems, and so they kind of retrenched and said, we're going to be more conservative. We've got new management in place. We want to do that. With Hitachi, what happened was we worked So first off, we work together with Hitachi and a company called Inabata. So Inabata is basically a company that mixes electrolytes. They're what's called a formulator. So they will take various compounds and mix them together, and then they will sell those to Hitachi and Sony and other companies, okay? And so what ended up happening was they decided to kind of split the risk. So in our last round of funding, Hitachi and Inabata both came through sort of at the same time to provide funding for the company. And in return, we synthesized some new molecules for Hitachi that they have primary intellectual property rights for. Okay, so they were getting something new in return. And then we've been working with them to basically to send them electrolyte. Okay, so we will send them electrolyte. They will do tests. The problem with this proprietary nature of the battery cathode and anode materials means that they will never send us cathode and anode material for us to test, okay? They will give us maybe some hints as to like what kind of graphite or what might be some of the properties of the graphite that we should think about testing, okay? But it's kind of an indirect process. So what we end up doing is trying to work with the customers a lot. So when they give us some kind of bad performance data back, we will try to understand what was happening and give them some suggestions back on things they might do. But in general, it's very secretive. And so what we try to do is just provide as much fundamental insight as we can to the company. And it just happens that Hitachi's getting quite good results. Yeah.
I wonder if you're aware of Professor Jim Davis, technical Japanese, who teaches great course here at the University of Wisconsin. And the other question I have for you is, we had 50 cycles instead of going like 2,000 or 3,000. Mm-hmm. Does that correlate so that you can get by with just doing 50 cycles?
So it turns out, so first of all, I don't know the person you mentioned.
Well, I'll
okay.
definitely get you in touch.
Okay, that would be good. In a coin cell, the problem is the geometry is very different. And for example, it's very easy for the electrolyte to get exposed to bare metal or bare stainless steel. So in general, people typically test coin cells out maybe to 100 cycles, okay? But in a development cycle, what you'd like to do is do as few cycles as you can and be able to project forward what the trajectory is. So most of the time, 50 cycles is plenty for us to know what the trajectory is like. And then, in a coin cell, 50 to 100 cycles would be the maximum. In a pouch cell, that's where you would start to get 200 or 300, 500 even cycles of a battery. And actually, we've had partners who have achieved kind of that level of cyclability, in more of a commercial environment.
So as I understand, one of the challenges with batteries is that they're still pretty expensive. Mm-hmm. I'm just curious, are there particular parts like cathode and anode electrolyte that particularly contribute to the cost, and like these organic silicon compounds be able to help out with that?
Don't know if they'll help out with cost. Okay, they will certainly help with safety, and safety is related to cost. So, for example, in an electric vehicle, you have pretty complicated cooling systems and a lot of thermal management of the battery that has to be put in place in order to avoid getting to temperatures where the electrolyte begins to decompose. So if you can make a more stable electrolyte, then in principle you can reduce the need for those cooling systems, which then result in cost at sort of the battery pack scale. Okay, at the scale of the battery itself, of the individual cell, it's pretty evenly distributed among a number of components. So typically, the current collectors are aluminum and copper. Copper is pretty expensive, okay? On the negative side, that's basically what's underneath the active material, okay, is a layer of copper. And then the cathode is graphite's pretty cheap. So the cathode tends to be most expensive because of the cobalt. So again, the driving force for going to some of these other materials is a reduction in cost of the cathode. And then, the electrolyte is a significant cost. And a large reason for the high cost of the electrolyte is the need to have it free of all water, right? Stabilizing an electrolyte and purifying it to that level requires specialized procedures that drives up the cost. So, it's conceivable that if we make an electrolyte that is more tolerant of water, that might actually, result in some potential cost savings there as well. I would say, it depends how you normalize things, but the idea that we can put in this new electrolyte at a 5 or 10% level and allow the battery to go to higher voltage means you store more energy, right, for effectively a nominal, tiny little increase in cost. So if you normalize the energy stored per dollar, right, then in principle you make out better by having a more stable electrolyte. But it's probably not the predominant factor, but the battery industry is really worried about the safety problems. For many years, it seemed like we had difficulty getting traction on the safety issue, because even our first generation compounds were more safe than a traditional electrolyte, but they didn't quite perform as well. And we found the industry would not even look at us if we couldn't make something that performed as good or better than a typical electrolyte, even if it was safer. So the big impact here is we now have something which performs even better than a carbonate electrolyte, can go to higher voltage, can go to higher temperature, and is more safe all at the same time. So getting that combination of properties, that is something that people will be willing to pay a premium price for.
I looked at smart batteries years ago, and the batteries were somewhat intransigent too, but wouldn't you think that would help in safety to look at some diagnostics? Real back here in town, people put pressure for their cadmium cells, so they charge them faster because looking at pressure. So is your company looking at any diagnostics within the battery?
So we do not do that ourselves. I mean, even if you look at something like a Tesla, a Tesla, the giant battery pack is made from small cylindrical cells, right? And part of that is a safety issue, so that if one cell decides to explode or decompose or something, it's only one cell out of the entire pack. And so they have some very smart management systems to monitor the temperature at the pack level, right? And to be able to do management and provide warnings if something bad is happening to the batteries. So in an electric vehicle, for example, that certainly makes economic sense to do that, and that is already being done. In systems like cell phones, I don't think they have active thermal management. They certainly don't have active thermal management. Whether they have sensors on them, that I'm not sure of, whether it will be cost effective at that level. They certainly have, for example, pressure release devices, so that if there is excessive gassing, instead of exploding, it will eventually vent.
This may be outside your core expertise, but you may hear from the wind what we do. Environmentalists are concerned about the mining hazards of some of the metals like lithium
Right.
and coal.
Right.
Do you have a sense of what are our future materials that are going to be more benign or availability or anything like that?
Yeah, I mean, you can use other metals like manganese, for example. There are other chemistries. So, for example, on the cathode side, there are materials like lithium iron phosphate, it's called LFP. That's a very stable, and that can be used in power tools. If you go out to Menards, you might find a lithium iron phosphate cathode. The challenge is for that, the amount of energy stored per unit weight is significantly smaller, right? So for mobile applications where you really want the most energy per unit weight, the idea is primarily to go toward, some of these other different transition metals, right? I would say the bigger approach from the overall sustainability problem. So one of the other challenges that I mentioned, that cobalt is pretty expensive, and so that actually may say that recycling actually might be economically viable. If you look at the overall, there are a couple articles I can point you to. If you shoot me an email, I'll point you to them. But there's a number of articles looking at the economics of recycling of these materials. And the problem is that as you go from cobalt toward nickel and manganese, they're lower cost materials. And so the economic driving force for recycling is even less. And so it turns out that it is less expensive to mine virgin material than it is right now, than it is to recycle the existing material. But part of that is there's not really a built-in infrastructure as there is for lead, right? Lead acid clearly has a good infrastructure for recycling. And so Tesla actually, which has the gigafactory on the Utah desert, Utah and Nevada, for doubling the worldwide capacity of lithium-ion batteries. About 3 or 4 months ago, they made an announcement they were going to build a very large lithium-ion battery recycling facility. And I think some of these exist, but it's not something which is necessarily mandated. I mean, I do know that the existing car companies, if you buy a car and you trade it in, they will take that material off your hands. But most of the electronic waste in this country, it probably gets put on a boat and shipped to some country that most of us don't visit very often, and where it ends up, maybe in a landfill where it's treated well, but maybe not where it's handled appropriately. So, but that's a really interesting problem, is understanding the overall economics of the recycling and how that plays into everything else.
We're a little over time, but thank you so much
Okay.
for your presentation.
All right. Welcome.